is a full professor of the Division of Biological Sciences, College of Arts and Sciences, University of the Philippines, Visayas, Miagao, Iloilo. His body of work includes research and lectures on mangroves, beach forest, and marine mycology. Among his most notable works would be a book co-authored with Dr. Jurgen H. Primavera, entitled Beach Forest and Mangrove Associates in the Philippines, 2012, and also the Handbook of Mangroves in the Philippines, 2004, co-authored also with Dr. Jurgen Primavera, J. Libata Ramos, and J.P. Altamirano. Both volumes received the Outstanding Book Award for 2013 and 2005, respectively, from the National Academy of Science and Technology, Department of Science and Technology, or DOST. In 2016, Dr. Sadaba co-authored another book entitled Mangroves and Beach Forest Species in the Philippines. In addition, he has also written numerous scientific papers published in national and international referred journals. He has made a distinctive mark in the academe, garnering innumerable citations such as the 2019 UP Alumni Association Incorporated National Distinguished Alumni in Environmental Management, the 2018 UP Alumni Association Iloilo chapter. He also has a lot of awards, namely Outstanding Professional Awardee in the Field of Education, the 2018 Chancellor's Award for Most Outstanding Faculty Professor Level, the 2011 Chancellor's Award for Outstanding Achievement in Research, the 2010 Chancellor's Award for Most Outstanding Faculty Associate Professor Level, and the Chancellor's Award for Outstanding Achievement in Extension and Community Service in 2007. In 2014, he won the prestigious award, Metrobank Foundation's Search for 10 Outstanding Teachers of the Philippines, Higher Education Level. He was Dean of the College of Arts and Sciences, UP Visayas, from October 2014 to October 2017. He also finished his BS or Bachelor of Science in Natural Sciences, major in Zoology, minor in Botany, cognate in Fisheries at the University of the Philippines, Visayas in 1983. His MS or Master's in Environmental Studies at the University of the Philippines, Los Baños in 1990, and his PhD in Botany, major in marine mycology at the University of Hong Kong in 1996. He is also a registered microbiologist and a diplomate of the Philippine Academy of Microbiology. Currently, he serves as a member of the board of the Microbiology Consortium of the Philippines under the Philippine Society for Microbiology. Ladies and gentlemen, let us welcome Dr. Resurreccion B. Sadaba.
Good afternoon, and thank you very much to the organizers of this year's Plant Biology Symposium. I'm very honored to be with you this afternoon to share with you uh, some of the things that I know on the role of mangroves in mitigating or reducing the impact of storm surges. So basically, my talk will follow this flow: introduction, what the mangroves, what tropical storm, what is a storm surge, and the role of mangroves in reducing the impact of storm surges. For several years now, we have seen the increasing risk to lives and livelihoods due to coastal flooding, and these are all attributed to the continued sea level rise and the increasing frequency and intensity of storms and cyclones. Primarily, all this as a result of climate change, and of course, the increasing population and asset values in our coastal lowlands. These are the destructive typhoons that hit the Philippines in the past 13 years. And I think among these, it is Typhoon Haiyan, or locally known as Yolanda, that is that really is considered to be the worst, no, super typhoon that hit the Philippines. And if you look at the data, it has the highest total damage estimate of almost 40 billion pesos, with the greatest number of fatality as well. And it seems that the appearance and the frequency of the super typhoons is now becoming the new normal. And if you look at these pictures, what can you see here? What is common in here? Well, it's very obvious that there is the loss of the protective green belts. Now, when you speak of the green belt, it's primarily composed of the mangroves, then you have the beach forests, and together they form a what we call a bioshield that protects the communities against the impacts of storm surges. Now, what are mangroves? This is a review. No? So mangroves are either the trees, or it could be the shrubs like your cantus. Then we have the ferns as well, and the palm. They grow in the adjacent, grow in or adjacent to the intertidal zone, and they are also characterized to be a very taxonomically diverse group that are also tolerant, many tree form that grow again in tropical and subtropical regions. Now, they also are found on areas where the average minimum temperature is never lower than 20 degrees. And you can see here, for example, and the entire Philippines is covered by mangroves. Now, what are tropical storms? All right, tropical storms are, or I would say rather, that the occurrence of the tropical storms in the Philippines is quite unique because the Philippines receives an average of 20 typhoons every year, and five of which are considered destructive. Well, for the reason that we are very close to the genesis location for the North Pacific typhoon. So we just have to adapt and adjust to this because this is part of our lives already in the Philippines. So if you look at this figure, you can see these are, the tracks of tropical cyclone from 1948 to 2016, when clearly there's an increasing uh, frequency of the cyclones that hit the Philippines, and you can see that the entire country is practically covered with these spaghetti lines that indicate the various tracks of the different typhoons of increasing intensity. Now, what are storm surge? So these are storm surges, or surge is a rise in the water level over the above in the predicted astronomical tides due to the presence of a storm. It's a tropical cyclone induced storm tides that can increase the mean water level up to 5 meters or 30 feet or more. Now, that's how do mangroves protect coast from storm surges? I say the role now of mangroves in reducing the impacts of storm surges. Now, in a study by Gedad et al., they have shown that they tried to analyze data uh, on the attenuation of wind waves and storm surges by the salt marsh and the mangroves. And they have seen that the mangroves are attenuated the storm surge, and so with the marshes. But if you look at the storm surge, the mangroves perform better in attenuating the wave height of the storm surge. Now, there's another paper. This paper uh, further concludes that both the mangroves and salt marshes can play an important role in reducing risk from coastal hazards. Now, what are the evidence that really mangroves are providing us with protection from storms hazards? There are two sources. One is based on direct observations of water levels during the event of an actual um, storm surge and the use of numerical models with varying levels or degrees of validation that simulate storm surge behavior either in the presence or in the absence of mangroves. Now, based on the observations of water level change, um, according to Granick in Rothenberg, 2007, observing this is a very challenging measure okay, during typhoons for the reason that the use of the equipment are the equipment they use are sensitive and it may be expensive and may be lost or destroyed during the surge event. Okay, and that is why they are only able to. The studies are usually limited only in the United States. Now, so very few studies really are available, like the work of Cross and et al. And Zhang et al. And again, one, although the other downside, perhaps if we look at it, is the fact that the measurements are only from South Florida. And because it's in the US, there is a restricted number of species. And compared to the more highly rare species in the Philippines or the rest of Southeast Asia. Now, in the work of Krause et al., they have really um, observed that indeed there was a reduction in the water level as the storm surge moved to the coastal mangrove ecosystem, but there is uncertainty on the relative contribution of the mangroves over the other types of wetlands like your salt marsh, open water, or microtopographic relief in this particular part of the world in the Gulf Coast over similar distances. Now, there are issues. One question is that how much is the contribution of mangroves to the reduction in the peak water level? That's because it's really impossible to control other factors that may have also affected the water level changes. And the possible solution is through numerical models. Because with modeling, you can play with many factors and determine and see the behavior of the storm source for better understanding. Now, so this numerical modeling has an advantage of being used as a complementary approach and really exploring the role of mangroves in reducing storm surge water levels. And usually examining the effect of the various parameters that you want to incorporate, like the width of the forest or even the species and many other characteristics. Now, one particular model is called the CIST. This was used by Zhang et al. In 2012. This is the coastal and estuarine storm tide model that used to simulate the passage of Hurricane Wilma. It was a category, almost a category 5 hurricane as it passed through over 200-kilometer stretch of the Gulf Coast of South Florida in the United States. And based on the study, they found the following one. There was a reduction in the model water peak level height. And in fact, it was a 10 to 30% increase in the water levels, however, in front of the mangrove cone compared to simulations without the mangrove. Then, this is actually a result where mangroves are actually act as an obstruction to water flow, like this one here also, and this front here, causing water levels to build up in front of them. And the increased friction within the mangroves can also lead to a steeper surge in front as the surge move inland. Secondly, they have observed that the simulation suggested that the storm surge was nonlinear across the mangrove width. No. So what are the factors affecting the storm source water level reduction? One is the very nature or the characteristics of mangroves in terms of the forest width, the tree density, and the structural complexity, the presence of the aerial roots, stems, branches, and the foliage, and of course, the whatever is the dominant species. And also it's influenced by the characteristics of the landscape. What's the surface topography of the mangrove? Are there channels, ponds, or pools? And the soil characteristics itself, the size and the forward speed of the cyclone, which may interact with the mangroves to influence the storm surge reduction. And Unfortunately, there are very few quantitative data available, and of course, according to Krauss et al., and that when data available is basically derived from numerical models rather than actual field observations. Now, let's take a look at the mangrove wind. So, usually, the report of the reduction is in terms of centimeter water level per kilometer, and it's usually measured in the direction of the travel of the surge. Now, and according to them, that constant attenuation rates, however, imply a linear reduction. Okay, it's a linear reduction, so it moves from very high, then it's just reduced. Unfortunately, this is not really true because the landscape in the mangrove is heterogeneous. Usually, you can find a mixture of channels, there are pools, and they vary topography. And, uh, and that is why we're saying that the underlying rate of reduction may not actually be linear, even if the entire environment were homogeneous. Now, in terms of the rate of reduction, Krauss observed that the observed water level reduction rate was between 40 and 160 millimeter per kilometer. And in the report of Shang et al., it could be as high as 40 millimeters per kilometer. It's validated numerical model. Now, in 2012, MacIver um, reported that the mangroves can reduce wind swell rates. So we're not talking in storm surge here. That 100 meter could reduce it from the height by from 13 to 66%. And if you have 500 meters, it could be almost from 50 to 99%. So simply because of the more obstacles, the better, because of the presence of the dense area systems and the branches that help attenuate the waves. Also, the effectiveness is further determined by what species are present, the age and the root structure, and the density and spacing. So, based on this illustration, you can see that the wave height decreases with the distance through is traveled through the mangrove. Now, in another study by uh, Shang et al. Also, they have shown that the water level reduction rate was highest in the seaward zone right here compared to the inner portion over, say, around 15 kilometers. So this is really where the main at the front there when the storm surge uh, hit this area, this is where we have the significant reduction over the greater distance. Now, if you look at the characteristics of mangroves, okay, another aspect that should be considered would be the density of the vegetation and the diameter of the area roots. So, of course, they have this are expected to be able to reduce the storm surge water level. So, the denser it is, the better would be its ability to reduce. Now, however, mangroves are very dynamic because usually the density of trees decline as it reaches the so-called climax or mature community. And like this one in Guimaras, this is already a mature community. You can see here, however, but there are very few trees, but they are very, very large. This one is dominated by the Soneracha alba. Now, another factor is that the distance traveled through the mangrove. So, wave passing through the mangrove forest will show an exponential reduction in height with distance. So, the farther it goes, the faster would be its, or the reduction is exponential. So, for example, the mean wave height over first 40 meters reported to be around 21%, then it to next 40, 17, and the total reduction 35 over the first 40 or 80 meters of the forest. Now, another important factor, in fact, would be the water depth and the structure of the mangroves itself. Let's take a look on the mangrove morphology also, because it determines the obstacles encountered with the waves as they pass through the mangrove forest, like the presence of the sprout roots of the rice opera. Okay? However, in here, Above the frontlets, the transom now present less obstacle if the water level is this high. But if it's just only here, then it is able to reduce the height and the energy also. And so the high wave attenuation at shallow depths, however, and then the reduction in the wave attenuation as the water becomes deeper and the waves are less affected by the prop. So if the water level is just up to here, then it's effective. But as it goes higher, then the effectiveness is reduced also. It's really dependent on the height and the distance. Now, so furthermore, as we know that mangroves, many of them have different kinds of area roots, and it has been observed that even for Avicennia marina, the nematophores of Soneratia alba, the Rhizopora, and that of the Bruguera, the wave reduction is greatest only at shallow depths, whereas in deeper water, wave heights are reduced less with distance, and more wave energy is disseminated. For in terms of the role of the trunks, the branches and leaves, again, this is particular for those species that do not have the area roots, like your Candila candle and Liver proticans. Well, of course, is expected only to be more effective in the shallow water depths only. Now, in terms of the age, again, it's very important because as mangroves age, there might be more areas developed. So the structure becomes more complex. But if it is not that complex, then water can easily pass through here, and there is no reduction at all. So when no obstacles are present, the attenuation of the waves depends on the bottom friction here. So so at greater depths, the bottom friction becomes less important. Okay, and there's lesser wave attenuation. In terms of the wave and height, for waves to enter a mangrove area, the reduction depends on the initial wave height until when the water reaches the branches and the leaves. Well, when there are no mangroves, then the wave reduction is not to be is independent because there is no obstruction. Now, the the role of the local topography is also important in the presence of the channels inputs like this one, because as we know, they're also affecting the overall pattern of flooding as they interact with the peak water level, and that will also influence the tidal inundation or the extent of the flooding itself. So, mangroves are said to be, according to Zhang et al., to attenuate a 2 to 3 meters storm surge from a slow-moving Category 5 hurricane. A mangrove forest with a width of tens of kilometers would be needed to attenuate. Unfortunately, for example, in the Philippines, we don't have any more, tens of kilometers of mangrove cover. And it's really, really a serious problem for many of our coastal areas. So the track direction of the hurricane also interacts with the local bathymetry to determine the surge characteristics. So what the standards are telling us that, you know, there are many factors that are interplaying, right? So we still need to dissect, all of this so that we are able to better understand, okay, the role of mangroves in here. Now, another aspect is that just like any vegetation, for terrestrial forest, for instance, that forest canopies modify near wind speeds, near surface wind speeds also. So, in summary, we can say that mangroves are important because they contribute to reducing loss of life and damage to property as a result of storms and cyclones via the reduction of the impacts of waves, storm surges, and even high winds. And for storm surges, so the more extensive they are, the better. Although it's only reported to be between 5 and 50 centimeter per kilometer, it's already, although small reduction, it's already great to reduce the flooding, in the low-lying behind the mangrove areas where communities are. And the movement of debris can also be reduced by mangroves because of the complexity of the root system and branches that will trap, uh, large moving objects. Um, so mangroves can reduce storms first of by slowing the water and reducing the surface waves. And measured rates is from 5 to 50 centimeter per kilometer. And in addition, surface winds are expected to be reduced. Surface winds to be reduced by more than 75% over 1 kilometer of mangroves. And of course, dense mangrove forests, particularly those species with airy roots, are expected to increase storm surge reduction rates. So we also consider the following characteristics that will help reduce the wave height and storm surge. The mangrove width, again, uh, the dilemma or the issue of linear attenuation as the rule of thumb versus the non-linear rate reduction. The characteristics of the forest itself in terms of the width, the density, and the complexity, structural complexity, the physical characteristics of the low area, particularly the presence of channels and pools, the topography, and the characteristic of the storms itself. So, on a final note, mangroves do not provide full protection. That is why evacuation and early warning are still essential. Thank you very much for your kind attention.